Okay, chapter 14, multiple integrals. We start with the section 14.1, double integrals. Okay, those can be found in this website, and we will today. We will start chapter 14, starting from the double integral, and the last section of this chapter is change of variables in multiple integrals. So now, double integrals. Okay, let f be a function of two variables like this, g is equal to f of x, y. Then, if we have a domain, AB times CD like this, AB times CD like this, then the function is defined on this domain like this. And if we want to find the volume underneath of this function on this domain, then we may find it by adding the small blocks like this, by adding all of those to do so. And if we explain one more, then we can divide the domain like the domain by pieces like this. Then we have delta x and delta y as the uniformed format like this, and at a point in the middle, and we may think a function value of the point. We may just point out the center point of this in this domain as a little Cij star. Then this f of Cij star times delta x and delta y gives us the volume of the one small block on in this graph. If we add all of those blocks on the x-axis and y-axis, and then we may define it as a capital S of n and m, which can be also written in this way. Okay, if we send n and m to infinity, which to make this domain very small, then we may write the limit of s of n and m when n and m goes to infinity. If this limit exists, then we may let it s. Then this s will means actually the volume of this two variable function on the top and the domain on the domain, so that we may have the volume of this object in this way when the limit does exist. So here is the definition of the limit and double integral. Let f be a bounded real function on a rectangle R. If the Riemann sum S and M defines above converges to a limit S independent of choice of the sample point Cij star, which was a center or some point in the small piece of the domain, then we say that f is integral over R, and we write integral of f of x, y dA on the domain R, or we can write it as a double integral like this, double integral of f of x, y dx dy on R for the limit S that we defined. Okay. If f of x, y is non-negative on a rectangle R, then this double integral represents the volume of the solid that lies above R and below the surface, g is equal to f of x, y, which means this volume, like this. Okay. And these are the properties of double integrals. First, it's the linearity. Okay. We can divide the integral in this way. And homogeneity, the scalar multiple can come out. And monotonicity, if the functions are always have this inequality, then double integral also keeps it. And furthermore, if f is continuous on R, and there exists at least one point x naught, y naught in R, such that double integral of this is same as f of x naught, y naught times the area of the region. Okay, this is called the mean value theorem for the double integral. So yeah, this is the one version of mean value theorem. And okay, now let's see the example 1. Let f be a function defined on here by f of x, y is equal to x. Show f is integrable, and hence we find this double integral. In this case, yeah, this is a function. So think about the Riemann sum with this each intervals like this. We have this n of 1 times n, 1 over n times 1 over m here, and at the point I star over n plug in here, which is exactly the same, and add all the way on the x-axis and y-axis like that. Then send. Then this partial sum is between since this is a strictly increasing function, so it's strictly it satisfies this inequality with the one value at I over n and less than or equal to at the point when we use the point I plus 1 over n here. And then if we send n, then this satisfies this inequalities. Okay, because the partial sum of I from I is equal to 1 to n is n times n plus 1 over 2. So we have this inequality. By Skidging theorem, if we send n goes to infinity, then this goes to 1/2, and this also goes to 1/2. So the limit of s and m goes to 1/2. So since the limit exists, we can say the value of double integral is as s is equal to 1/2 like this. So this we use the Riemann sum concept to find the double integral at this point. And now we think the double integral over a general domain like this, not just rectangular domain. Then f and let f be a continuous and bounded function on an arbitrary domain in R2, and let R be a rectangle which contains D. Now we extend f on D to a function f star defined on R as follows. The function value is the same on D, and if xy is not in D but in R2, then we define the function value as 0. Then f star is bounded and continuous except on the boundaries of D. This f star is defined on R now. Okay? Then, if f star is Riemann integrable on R, then we say that f is Riemann integrable on D as well. Okay? So, when we try to find the double integral on D, we may have the same value by the double integral of the function f star on R instead of D. So with this modification of the function from f to f star, we can use the same the Riemann sum technique to find the double integrals. Okay, next, iterate the integral. Let f is an integrable function on R, and we define this function as a Riemann integral of one variable if it exists. Okay, then we may think we may integrate this function which is a of y from c to d with respect to y like this. Then we can write in this way. And similarly, we can integrate the function of f of x and y with respect to y first, then x next. It turns out that in most of the case, the two iterated integrals of this and this are same. When f is a continuous function on the rectangular domain like this. This was shown by Pubinis in Okay, in 1907. The Fubini theorem says that if f is a continuous function on the rectangular domain R, then we can change the order of integration without the changing of the value of the whole double integrals. And this Fubini theorem tells us that we can really use the 3D computer without hesitating to produce this 3D object by layers of the two-dimensional object. Okay, next. Evaluate the integral. Okay, in this case, we do integrate this first with respect to y. So, the antiderivative of this is y plus 2xy squared. And then we do integrate this with respect to x. So this gives so that this means 2 plus 16x. So it gives us 2x plus 8x squared from 0 to 1, which gives 10, which also can be computed by this Sage code, okay, which is 10. Also, if we do integrate this one with respect to x first, then y, then this antiderivative of this with respect to x is x plus 2x squared y, and then find this which is 1 plus 2y instead of 2 plus 16x, and we do integrate this with respect to y from 1 to 3, which gives 10. These values are same. Sage code of this integration gives us the same value of what we are looking for, which is a 10. Okay. Anyway, yeah, the iterated integration works for that. Here is another example. Evaluate this double integral. Then, by iterated integral theorem, we do the integrate this with respect to x first, and then y next, which gives us 7 over 12 as the value. Okay, with the Sage code of this x squared cube plus y squared, to integrate f with respect to x first from 0 to 1, then y next from 0 to 1. Then this command gives us the same value of what? 7 over 12. Okay, you see? Okay, integrate x cube plus y squared. We do integrate f with respect to x from 0 to 1 first, then integrate this one with respect to y from 0 to 1, which gives us 7 over 12, which we had. Okay? Next example, evaluate the integral, double integral, next example. Okay? Evaluate the double integral x cubed plus y squared on this region. Okay? On this region. Okay, then by Fubini's theorem, yeah, we can integrate x first or y first. We can choose whatever we like to do. So we do just integrate the x first. Then we should figure out the domain that we are integrating. So the domain is what? Is domain was given as an x is between 0 and y is between 0 and 1. So y is between so 0 is between 0 and y, x is between 0 and y is between 0 and 1. So this is very clear. So we just do the integration which have with respect to x, then y to get 3 over 10. And actually this graph shows the domain for the next example. Evaluate double integral of x on the domain D, where R is the region bounded by the parabola y is equal to x squared, and y is equal to x plus 6, like this. This is the domain D. We want to integrate this function x on this D. Okay? Then, D can be written as, so we figure out the points that they meet. So we integrate the x-axis y-axis first, then we do integrate. The region can be represented in this way. Okay, region can be represented in this way. X is from -2 to 3, and y is above this, which is x square, and below y is equal to x plus 6. So this can be written in this way. Then we do integrate the function with respect to y first, and then do the integration with respect to x next, because we have a variable here first, then constant here next. So the Fubini theorem gives us a freedom to choose what to do integrate first. Okay, so we just do integration of x with respect to y on this, from x squared to y x plus 6, which is this. Then do integrate this with respect to x from -2 to 3 to have 125 over 12. Okay. Okay. Next example shows evaluate this function with respect to this. Since we know the algorithm, and also we can draw the graph of it, like what Mr. Lee in-hand showed before, then we can draw the region without much difficulties. And also we can do the computation by hand as well as by using the Sage code. So here we may do the integration by computer algebra system. So we do integrate x times sine x times cosine y. We do integrate this with respect to x first from 0 to pi, and then integrate this integrand from 0 to 2 pi with respect to y. And that will give us pi. Okay? So we do integrate it. And as you see, we do integrate it. Then this gives us the answer pi, like what you have. The same comment and things. If we do integrate the x first, then we have this pi answer. If we do integrate the integrand with respect to y first, then do the x next, then it also gives us the same answer pi. Okay? And next, change of the order of the integration. Okay. And for a domain that can be thought of type 1 as well as type 2, the domain D can be written in this way, and the same domain can be written in this way and this way. Here we have constant, here we have constant. Then with those, we can rewrite this double integral in this way and this way. It is often useful to change the order of iterate the integrals. Okay. Okay. Next example asks us to evaluate the integral, double integral of this one, on this region. There was a typo here, so I fixed it. So in this case, we can easily find this by just integrate this integrand with respect to y from x to 1, and then to integrate all this with respect to x from 0 to 1, which will give us the answers like this. But also we can change the order of the integration by drawing the domain in this way, like this, or this way, in this way. So we can do integrate this integrand with respect to x or y by Fubini theorem to get the answers as 1/4, like we see. Okay. And next, evaluate this x minus 1 with respect to x and y on the region R, which is enclosed by y equal x and y equal x cube, like this. Y equal x and y equal x cube. So we are integrating this object on this region. Okay, so this R can be written as this union this, and this R1 plus R2. So we have to do integration of this function on R1 and R2 by the theorem that we have seen. Okay, and this region R1 can be written in this way, and this region R2 can be written in this way. So we do the integrations like this, and by adding those two to have minus 1.5. Okay, so this integration can be done in this way. Do the integration, first one here and the second one here with the same function, and this can be simulated in here to have the answer minus 1.5. Okay, which is the answer. And also here we found one errata that says this should be an x instead of y. And thanks for the pointing out. And next example, areas of region by double integrals. An area, this area D can be found by a double integral like this for the constant function 1. And this example shows find the area of the region D enclosed between the parabola and the line y is equal to 2x, like this. We want to find this area by double integral. So in this case, this region can be written in this way, and this area can be found the double integral of 1 with respect to y from 1/2 times x squared from there to 2x, and integrate that integrand with respect to x from 0 to 4. So this double integral will give us the 16/3, like you see here, which is the this area. So double integral can be used to finding the area of the region. And average value of a function in plane. And this is the definition of the average function of the integral of one variable function. And now this can be extended for the two variable function case like this. The double integral of this divided by the area of R instead of just b minus a. That gives us the average value of the function of two variables. So find the average value of this function of two variables over the region R like this. Then what we need to do is we need to find the double integral and find the area of R and just divide it. That will give us. Okay, in this case, because it's rectangles and actually right rectangle, so we have the region, the area of the region. Here, this area of the region. So the area of the region R is 4, then the average value F is, average value of F is, this can be found as 1/4 times double integral of this one. This double integral can be easily computed with respect to y from 0 to 2 and with respect to x from 0 to 2, which can be easily computed, which is as 8. Now the application of double integrals. This double integral can be used in the probability, for finding the probability, and this if f of xy is a joint probability density function that satisfies this, then the double integral of this function, joint probability density function, should be 1, and if f of x, y is be the density function at the point x, y, then the total mass m of the given lemma in the domain D can be written as this. In this case, the center of the mass, x bar, y bar, can be defined as this integral divided by the total mass, like this. So the double integral can be used in physics and probability and statistics and social science and engineering as well. Now you have the problems in section 14.1 double integrals and solutions and the computational tools to solve the problems like this. Okay, so so hope it can help. I think that's the end of the section 14.1. Okay. Do you have any questions?